discuss about the concept of a probability. Probability is a long discussion. That's why we have to discuss two parts. The one part is part 1 and second part is part 2. But today we have to discuss about only the part 1 part. But before that we have to discuss the whole total probability. What are they? We have to one by one we have to say today. Part A consists, first one is the probability of an event details. Next one is the axioms or postulates of probability. Next one is the rules of a probability. There are 6 rules. Next one is the conditional probability and their examples. Next one is the multiplication rule of 2 or more events. Next is the independent event and their theorems with suitable examples. And the last one is Bayes theorem. Part 2 consists probability distribution and probability densities. What are they? A very important for 12th class onwards. First one is random variable, and there are 2 types of random variable, that is the discrete and continuous random variable. Second one is the probability distribution of a random variable. For a discrete case, we have to say probability mass function. Second one, the probability distribution function of a random variable. For a discrete, the distribution function or cumulative distribution function. Probability density function of a random variable. For continuous, say that is the probability density function, or we say density function, or exactly that is density. The next one is the multivariate distributions. Next is the marginal distributions. Next one is the conditional distributions. Mathematical expectations. Next is moments. Moments, different way we have to find out the standard deviation, variance, Chebyshev's theorem, marginal moment generating function, skewness and kurtosis, product moment, moments of linear combination of random variables, etc. Next is what is conditional expectations. We have to find out the mean, standard deviation, variance, and etc. Next, spatial probability distribution. There are exactly same type, that is a discrete, another one is continuous. Discrete uniform distribution. We have to find out mean, median, variance, moment generating function, and so on. Binomial distribution, mean, variance, moment generating function. Negative binomial distribution, similar way, mean, median, variance, etc. Geometric distribution, similar way, mean, median, variance, etc. Same meaning as mean, median, variance, etc. Another one, very important, is spatial probability densities for BSc level and higher level. Uniform distribution, what is that? Uniform distribution, gamma distribution, exponential distribution, chi-square distribution, beta distributions, and also some spatial distributions, Cauchy distribution, Rayleigh's distribution, Pareto distribution, Weibull distribution. Now we have to discuss one by one. For part A, before probability of an event, we have to go to sample space. What is sample space? Now the set of all possible sample points or outcomes of a random experiment is called the sample space. Already discussed what is random experiment. For coin, for die, for a pack of cards, these are the random experiment. And it is denoted by capital S or omega. Suppose a coin is tossed, then sample space S equals to H comma T. Then what is the number of sample space? Now equals to 2. Mod S equals to 2. Similar way, how can you find the sample point, or who can say the element of the sample space? For above example, H is a sample point and T is also sample point. There are two sample points. Next one is event. Any subset of proper subset of a sample space is called an event. Suppose S is a sample space and E is a event, then E is a subset of S. That is, X belongs to E, that means X belongs to S. Random experiment means that is a trial. Well, the performing of a random experiment is called a trial. Discrete. Random experiment, there is a sample space may be discrete or sample space may be continuous. In a sample space contains a finite number of elements or infinite though countable numbers of elements, then it is said to be a discrete. But all points are line segment or all the points in a plane, then it is said to be continuous. Mutually exclusive events. If A and B are two events, suppose A intersection B equals to 5, then we say A and B are mutually exclusive events. Suppose A and B are mutually exclusive, and that means also as a incompatible events. What is impossible event? Suppose impossible event means there is no elements, there is no sample points that can written as 5 and x such that x not equals to x. Suppose a coin is tossed, how many sample points? Now 2 sample points. Then what is the sample space? Now S is equal to H comma T. That means a coin is unbiased. That is called honest coin. That is called fair coin. That is called perfect coin. Unbiased coin or fair coin, what is the meaning of that? Like coin is said to be unbiased if it is made of a homogeneous material and it is the center of a gravity is at the center of the coin. Otherwise, it is called unfair or biased coin. Next, go for the probability of an event. A is an event of a sample space. Then probability of an event is denoted by capital P of A. The number of favorable cases by number of exhaustive cases. That favorable number of elementary events by total number of elementary events. Also say that number of outcomes that make an event by total number of outcomes of the experiment. But when outcomes are equally likely, equal chance of occurring, then whenever the probability of the event, you have to find out there must be outcomes are equally likely and equal chance of occurring. Already said equally likely or equal chance of occurring. And that is called as mod A by mod S. The number of A by number of S. Also it can be taken as order of A by order of S. Probability of a sure event equals to 1 and probability of an impossible event equals to 0. By S equals to 1 and that is called probability of sure event. Then that means S is a sample space, also is called as sure event because the S event and sample space both are equal. Probability of an impossible event, if phi, then P of a phi equals to phi mod by mod S equals to 0. The next one is the postulates or axioms of probability. There are postulates are the probability of an event is a non-negative real number. The probability of it must be greater than equals to 0. And another postulate, the P of S equals to 1, that is sure event, probability of sure event. Another one, suppose A1, A2, A3 is a finite or infinite sequence of mutual exclusive events. Then P of A1, A2 up to A3 equals to P of A1 plus P of A2 plus P of A3 and so on. Exactly union can be taken as plus. So P of A1 plus A2 plus P of A1 plus P of A2 and so on. If A1 and A2 and A3 are mutually exclusive events. They are disjoint sets. Some rules of probability. There are 6 rules. Rule 1. P of A dash equals to 1 minus P of A. Whenever the A is the event, of a sample space, just S minus A equals to A dash. That is a set theory. S minus A equals to A dash. A dash means the complement of A. And so P of A dash equals to 1 minus P of A. And the simple proof, you see that the proof. Very simple, and just remember it. This is the very important proof. Just see the proofs. Not describe it, but you see the proofs in my notes. P of phi is equal to 0. You know already probability of an impossible event. The phi is a subset of S. We know phi is a subset of S. That means that is a probability of a phi must be subset of probability of S. Probability of a phi is less than equals to probability of a S. Probability of a phi. So probability of a phi equals to 0. Next one is rule 3. Already proof is here. Rule 3. If A and B are events of a sample space, if A is a subset of a B, then P of A less than equals to P of a B. Must be probability of A must be less than equals to P of a B is here. And similar other way we have to prove this in this way. Another one, rule 4. P of A lies between 0 and 1. Very simple proof. Suppose case 1, if A is equal to phi, then mod A equals to 0, then P of A equals to 0. This is case 1. A not equals to phi, then mod A greater than 0, then P of A equals to mod A by mod S. Must be probability of A greater than 0 because the postulates, then so P of A greater than equals to 0. Case 3, A is a subset of S, mod A less than equals to mod S, P of A equals to mod A by mod S, must be less than equals to mod S by mod S equals to 1, therefore P of A less than equals to 1. After 3 cases, the P of A lies between 0 and 1. Very important proof, and maybe in the exam. In a sample space S, then P of A union B equals to P of A plus P of B minus P of A intersection B. Already proved. We have to prove this, and the other way we have to be also prove this. 6. If A, B, C are any 3 events in a sample space, P of A union B union C equals to P of A plus P of B plus P of C minus P of A intersection B minus P of A intersection C minus P of B intersection C plus P of A intersection B intersection C. Very easy example and easy theorem, also easy proof. What is conditional probability? Before conditional probability, first one we have to know about P of A equal to mod A by mod S. S is finite. Case 2, omega equals to S is countable. So P of A equals to this symbol. Summation omega belongs to a P of omega by summation omega belongs to sample space P of omega. Where omega has the weight, P of omega is equal to P of this. This way we have to write. Case 3 is relative to another S. So A intersection S is equal to AS. A intersection S must be taken as AS, is relative to S. Case 4, P of A minus S is equal to P of A intersection S by P of S. If P of S, because it is a ratio and it is a numerator and P of S is a denominator, then P of S must be greater than 0. It's called the conditional probability of A relative S, and P of A not equals to 0, then the conditional probability of B given A, that means P of B minus A. Probability of B given A, P of B minus A, and P of A intersection B by P of A. Multiplication rule. If A and B are any 2 events in a sample space, P of A not equal to 0, P of A intersection B equal P of A into P of B minus A. Similarly, if P of B not equals to 0, P of A intersection B equals to P of B into P of A minus B. Similar 3 events. P of A intersection B intersection C equals to P of A into P of B minus A into P of C minus A intersection B. Easy proof and using theorem, that is 2.9. Multiplication rule of n events. So exactly P of A1 intersection A2 intersection AN, P of A1 first, P of A2 minus A1, and next P of A3 minus A1 intersection A2, and so on dot dot P of an minus a1 intersection of 2 intersection a n minus 1, provided this not equal to 0, that means greater than 0. And very easy example, and by using the method of induction you have to already be proved. Next one, the independent event. If a and b are independent, means P of a intersection b equals to P of a into P of a b. Neither P of a equals to 0 nor P of a b equals to 0. Dependent event means P of a equals to 0 and P of a b equals to 0. And for the exam, if a and b are independent, then we have to prove a and b dash are also independent. P of a intersection b dash equals to P of a into P of a b dash. Very, very important for the exam. Very, very important for the exam. If this way, we have to prove this. Similar way, if a and b are two independent events, then a dash and b dash are also independent. So P of a dash intersection b dash equals to P of a dash into P of b dash. Exactly same way we have to prove this. Exactly P of a dash intersection b dash equals to P of a dash into P of a d dash, and a dash and b dash are also independent. If in this way we have to prove this, and a dash are very, very important for the exam. And also the more than two events. Exactly P of a1 intersection a2 dot dot intersection ak equals to P of a1 into P of a2 into dot dot P of ak. ABC are said to be independent. That means P of a intersection b, P of a into P of b. P of a b intersection c, P of a b into P of c. P of c intersection a, P of c into P of a. P of a intersection b intersection c, P of a into P of b into P of c. A, B, C are independent. A will be independent of any event formed from B and C. That means A is independent of B union C. How can you prove this? Now P of A intersection B union C equal P of A intersection B union A intersection. By set theory, you have to easily prove P of A into P of B union C. Next are base theorem. If B1, B2, Bk constitute a partition of the sample space, P of Bi not equals to 0, then for any event A in S, P of A not equals to 0, then P of Br minus A equals to P of Br into P of A minus Br whole divided by summation P of Bi into P of A minus Bi, summation I equals to 1 to K, and R is equal to 1 to up to K. And very important, the partition of the set already said in the set theory, and so not discussed here. So P of A equals to summation I is equal to 1 to K, P of Bi into P of A minus Bi. We have to take it in right side. Just right side you have to take it and just put it the value of P of Br into P of A minus Br and summation this. So P of A into P of Br minus is just multiplied and P of A, and now the P of Br minus A. That is right, left hand side. Hence proof. Very easy and very important for the exam. Base theorem. Now the part A is concluded, and after that we have to discuss the part 2 in next day. Before that, I request to all the students belonging to the 9th class to up to MSc students, a very important the concept of the probability we have to remember, and the notes and examples, very, very important for the students, for the exam, for the higher studies, for the PhD levels, and very, very important for the exams. Most important. Thank you very much.